You want this one? All right, guys, we went to a commercial there for a minute. Everybody sign this?
No.
Nope. So, here's the addition of Br2 to an alkene. What does it produce? Vicinal dihalide through the formation of
Bromonium ion.
Bromonium.
Ion.
I'm going to show you what that bromonium ion is.
It does form a carbon.
Do you want another color? Is that purple?
I got colors. Maybe later, okay? Let's see if this one works.
Does this not form a carbon cation?
What are you talking about? What carbon cation are you talking about?
Does this form a carbon? Oh no, it did.
Okay? So, here's what happens. Now, before, you had an H on one side, yes? And a Br on the other side.
Right.
And this double bond attacked the H because the H was delta positive. While that one was delta
That's a negative, right?
This one is going to attack it anyway. Okay, even though this doesn't appear to be positively charged. There are two ways of doing this. We can do this on one step, or we can kind of do it in two steps. What do you like?
2 steps.
1 step or 2 steps?
2 steps.
You like 2 steps? So, this double bond is going to
Attack
attack that bromine.
that.
Of course, the bromine now will have a bond with these 2 black electrons, yes? These electrons are black. Attacking that bromine. And now, can this bond stay here?
Nope.
No.
This bond cannot stay there. So that bond with the 2 electrons are going to leave with that bromine to form bromide. Yes? Now, if this attacked, this is going to look like this. We are going to place this new bromine on this carbon here. So this is going to look like that. We are placing the bromine Oops, you guys forgot the R, huh? Okay. Now, what is this going to be?
Carbocation.
This is going to be,
Carbonium.
this is going to be a positively charged
Carbon.
carbon. Yes? I don't want you to say through the formation of a carbocation, because this does not follow the regular idea of a carbocation being planar. Okay? So, this carbocation is a intermediate resonance structure here. It's not stable. So, what happens is, because these electrons are so close together, these electrons are actually going to go there and make a bond. So this is going to look yes? Now what are the formal charges on this carbon? Formal charge on this carbon? 0.
Neutral.
Formal
Yeah.
carbon this 0.
Neutral.
This carbon, 0. Formal charge on this bromine is positive 1. So this will have a positive charge there. And this is called a bromonium. Bromonium ion. Let's write it somewhere else. Let's write it here on the side. Bromonium ion. This is the idea of this reaction. Okay? Yes.
Does that have anything to do with like something that they say about like a cap or
Like a what?
a cap? Like
Cap?
yeah.
What type of cap?
I don't know,
Like bust the cap?
yeah, something like that.
No, not busting the cap. There's no cap busting here. Okay? I don't know what it is, but there is a formation of this here, which is stabilized by the electron pair on this bromine. if the bromine would have gone to this carbon, it would have had to stabilize it on that one. So what happens is, this positive charge, this is kind of a resonance structure, and the positive charge is shared between all of those, okay? So, about the cap, I'm not sure about what cap. And this is called the what? Bromonium ion. If this would have been with Cl2, this, instead of being called bromonium ion, it would have been called?
Chlorine.
Coronial.
It will be called a chlorinium ion.
Chloranium.
Because it's chlorine.
Yeah.
Chlorinium
Chloranium.
ion. Not chloronium ion. So, bromonium ion is for bromine, and chlorinium ion is for?
Chlorine.
Chlorine. Now, tell me, what else happened? What else happened here? There was a formation of
Bromine.
bromide, yes?
Bromide, yeah.
Now, this is bromine, this is bromine,
Uh-huh.
this is bromide, because it has
A
a
negative.
negative charge, and
Yeah.
this is bromonium ion,
Right.
yes? So, what is going to happen is,
It's going to attack it from the bottom.
this, not the negative charge, right? The negative charge is just,
Yeah.
the electron pair is going to attack either this
All that.
or this carbon, yes?
Yes.
Let's say it attacks that carbon.
So
Now
the bond
here,
is gonna
I did
break.
not have a reason why to either attack this or that, right?
No.
I just drew it there, but there is a reason why one would attack over the other. And if it attacks there, what you get is this. There is a carbon here. Now this bromine is on the top, yes?
Right.
Do you see it on the top?
Uh-huh.
I see this bromine is on the top, and that is that way and this way, and that way and that way is that.
Uh-huh.
And the next bond occurred
Through
through
the bottom.
the bottom.
Right.
And
Anti.
this is how this would look like.
Yeah.
One bromine is on the top, and one bromine is on the bottom. That is called the anti-addition.
Anti-addition.
Anti-addition means, actually it's anti-periplanar or anti-coplanar. I like periplanar. It sounds more intriguing, yes? Periplanar means that this here and that here are on the same plane. So this is, if you look at the Newman projection for this, how is that going to look? The Newman projection. Do you guys remember Newman projection?
Yeah.
Of course.
Mercedes-Benz, huh? One BR is going to be here,
Yeah.
and the other BR is going to be there. This means
Anti.
in the same plane, an anti. So this is called anti-periplanar.
Oh, nice.
Now, the attack here, I want you to make a note. The attack here, this bromide, or not this bromide, if anything that will attack here, if there is a choice of attack, it will attack the carbon that has less hydrogens on it. Because a resonance structure of this would look like this. Where should I write this? Can I write this somewhere else? I'm messing up the picture, yes? Let's say here, I have a carbon and a carbon. And here I have a hydrogen and another hydrogen. And there is this bromonium here. The nucleophile that will attack, and let's say that the nucleophile is not bromine because you can't tell the difference between them, yes? Let's say that the nucleophile was something else. Which of these two carbons will have a larger partial positive on it?
The one on the left.
Which one is
The
more
one on the
stable?
left.
That one left.
This
Yeah.
is more stable.
Yeah.
This carbocation is what?
Stationary.
1, 2,
Two,
and
three.
3. This is
Tertiary
tertiary
carbocation.
carbocation. But if you make it like this is a what carbocation? This is a primary
Primary.
carbocation. So the attack is always preferred where there is, or where there are more carbons. Yes?
Mm-hmm.
That's not going to happen now, but in one of the next reactions we are going to do, you have to show the attack on the right carbon. Okay? Here it doesn't make a difference, yes?
Nope.
Why is one of them tertiary and the other one primary?
Because this one here has 1, 2, and 3 carbons attached to it,
Yeah.
and this one has 1 carbon attached to its primary. How do you like that, guys?
That was nice.
That's cool. You're dying to show me that you can do that on the test, right?
Of course.
I'm dying to see it. So what type of addition was this?
Anti-addition.
Is this like related to Markovnikov?
No.
It's not related
No.
to Markovnikov, this is anti-addition. So whenever you draw this, if there is a way, you have to show me that this bond is opposite to this bond, yes?
Right.
To show that anti-addition. Let's try this. See what you can make of this. Here we have this. And you are going to draw this Br2. And you're going to have a problem if you try to do the intermediate for this. So you have to have in your head that what is going to happen is the bromine is going to add to 1 carbon, and the other bromine is going to add to the other carbon. And the addition has to be anti. So you draw.
Look, Professor, try erasing a piece. I brought them.
Wait, what? You dry stuff with this? What did you dry in this?
Yeah.
The mechanism is showing, and the product is just what you get the result. I'm gonna know that.
Smells a
Because
little.
doing these arrows, that signifies that's the mechanism. But just the product is just the answer without doing the arrows.
Okay, we're going to put this to the test. I think you used this twice, didn't you?
No, just once.
It's very thin. By Mickey Mouse stuff.
Maybe you can layer them so
Damn.
wow. It erases nicely.
New discovery.
Sophia, you're the man.
Whoop.
All right. Let's erase this, yes. You guys still writing this?
No.
Elizabeth, are you still writing this?
No.
How many times you watched the video? Huh? Once?
It's like cleaning the board. All the mess from before is gone. Still kind of
I feel early, you know. I feel like a man. All right. So tell me, what is the answer to this? So you do not write the double bond, yes?
Right?
Now, if you go like this, like we have done in the past, yes? In which we say the BR is here and the BR is here. I give you some credit, but I'll take some off too. Okay, because you have to know that this addition, put a methyl group here. You have to know that this addition here was what? Anti. And you have to show me that when this adds to this cyclohexane, what are you going to have? You are going to have
one in the
this
front, one in the
stuff,
back.
one in the front,
One in the back.
one in the back.
Yeah.
Okay? And since the addition was anti, if I put one bromine here, where's the other bromine
In the
going
front,
to go?
on the bottom. Right?
Where, here?
No.
The weight.
No. If this is dash, this will be on the wedge.
Front, right.
Okay? Yes? And that's there. What's happening? You're hyperventilating. Just relax, it's going to get a whole lot worse. Okay? What else can we draw? What happens if I do this? And instead of putting the bromine here, now I put the bromine here. And then I put, does the other bromine go here?
No.
No, the other bromine
It goes on
goes.
the bottom.
Here.
This is in the back. Yeah.
Okay?
What was the point of adding the methyl group?
Yeah, point.
Yeah, like why did you add it afterwards?
I just felt like adding it. Okay? So, what are these two of each other?
Enantiomer.
They are enantiomers. Okay? They're enantiomers. What is this? Is this 50-50 or is there a reason why it's preferred over the other?
No.
No, so we are going to say this is a
Racemic mixture.
racemic mixture.
Nice.
So on the test you have to look to see if it gives you enantiomers or if it doesn't. If it does, you have to draw them with a dash and a wedge.
Oh, okay.
Okay?
Alright.
Probabilities are that what am I going to do?
We're gonna put that on the test.
Ask you for the dash and the wedge.
Mhm.
Okay?
So when is it not a racemic mixture? Which is not 50-50. But when would it be a mixture that's not racemic? And when it's favored over
When it's
the
not chiral.
then how do you know which one is favored?
How do you know which one is what?
Favored.
Since it's not chiral, they're both the same.
So either you have racemic mixture or you only have one.
All right. I don't want you guys to find shorthands of doing things.
Mhm.
You draw the silly thing, okay? And there is a chance of drawing it on one side and a chance of drawing it on the other side. So what do? You draw them on both sides.
Right.
Don't imagine, oh, what if he gives me this? What if he gives me that? Okay? We already discussed this many times.
Are all enantiomers racemic?
No, not all of them are racemic. They're racemic in this case and racemic in the other case. Okay? Yes?
You can show what's
Methyl combo.
Drawing that form, you'll see there, the intermediate. So draw the what? What's the intermediate?
Chlorine.
Chlorine. Chlorinium.
Draw the chlorinium ion, intermediate, and then show the attack from one side and show the attack from the other side.
Oh my gosh. Okay. Attack.
Yeah, attack. The attack here is from the where? From the opposite side, yes? Why don't you humor me and try? You afraid of failure?
No, I just know where it's going to separate.
So, how are we going to do it?
You want to wait till it.
You are going to
Without-
redraw this thing here, yes?
One bond.
Yeah. Without the double bonds.
Without the double bond. Where do you want to place this chlorinium ion? Does it matter if I place it on the top or I place it on the bottom? Does it matter?
No,
No.
it doesn't.
I can do it like this. Yes?
Yep.
Yes or no?
Nice. Yep.
And the other one is the Cl minus. Is going to either attack here or
Attack the other one. Yeah.
attack there. No matter where it attacks, you are either going to get, you're either going to get a chlorine here, and the other chlorine is going to be where?
Another
The
side.
other chlorine is going to be here. Or you are going to get a chlorine chlorine here and the other chlorine
Down.
Down, yeah.
Yeah.
down there.
Wait, why does one have to be up and
Yep.
the other down? Because it's anti. Oh. And why did that little, like, triangle have to go inside of the pencil?
It didn't have to go inside. It could go outside.
And do we need to show, like, the addition of the first chlorine, and then the
Well,
attack of the other, and
if
then
I-
the attack of the remaining chlorine?
If I ask you, yes. But if you would have drawn this like this, which is okay too, yes?
Yep. Same thing.
Where are you going, La Vista? You got a small bag? So, either attacks here or
Tax. The other one.
attacks there.
Yep.
But if it attacks here and there, what do you get? The same thing.
Same thing. Yep.
Okay?
Would it be wrong to have like the back
Would it be wrong if you did what?
have that on the chlorine? Like how you have it going up and down there instead of having the dash around and then.
No, if you draw the dash correctly, it's not wrong. But this picture was kind of three-dimensional in the way that it is drawn, so that's why I drew it like that, so you guys get used to. This is 3 dimensions. Can you see that this looks like kind of flat? I tried.
Wait, so you just drew that bottom one just to make sure that it's okay to do a triangle?
Yeah, you can. It's not called a triangle, okay?
Oh, I know, to draw.
It's called the chloranium ion. It sounds smart as that. So we're trying to look smart in this class, okay?
Yeah, then it was complex, and then it loses an electron, and then it explodes the bottom of the house.
What else?
But then this becomes outside of the house, so this comes inside the house. So then we're doing it so then we go to the inside, so it's one goes to the bottom of the house.
Okay, let's do another one. This reaction is called hydration.
Hydration.
We are going to do dehydration when we do eliminations. But yes, we are, but not today.
Swan said he was coming today.
So here is the general equation. Guys, here's the general equation. Now what we are adding is,
Hydrogen. Water.
this is H2O,
Uh-huh.
which is water. It has a side that is positive and it has a side that is
Negative.
negative. We are going to have to use here H2SO4 catalytic amount. So this is a catalyst. This is not a very good synthetic reaction, but I show it to you so I can show you the mechanism once again. So you guys enjoy mechanisms. Yes?
This is acid catalyzed hydration.
So what we are going to get here is, what's going to happen?
Let's have the hydrogen.
One hydrogen is going to add to one side and the OH is going to
The
other
the other side. Okay? This is like before, it was a Br and a Br, or an H and a Cl.
Mm-hmm.
They all look the same, do they not? So it's not like you have to memorize everything again and again. So on one side, you are going to have a hydrogen, and on the other side, you are going to have the OH. This H and this OH is water. This is why this is called hydration.
Mm-hmm.
Yes or no?
Yes.
Now, I did not show any stereochemistry here. This is just to show you that one OH goes to one side and the other to the other side. This follows Markovnikov addition.
Mm-hmm.
And of course, the addition here is like the addition before, where the hydrogen goes to one side, and what do you form on the other side? A positive. Because you form a positive on the other side, this occurs through the formation of a carbocation. So if it occurs through the formation of a carbocation, what can we possibly have? If the center is chiral, we can have a racemic mixture. Yes or no?
Yes.
So this is more of the same. You want to try one?
Yes.
The example you gave, it wouldn't be anti-sin. The first example you did. It
Which
wouldn't-
here?
Yes.
I have not talked about this at all.
Okay.
No anti, no sin.
But which is why I'm asking why you said put it as anti.
I put it as sin so you can see.
Put it as sin, yeah.
Yeah. So you can see the OH and the H, that it comes from water.
So the H2SO4 doesn't really affect it, it's just the catalyst.
The H2SO4 is a catalyst.
Catalysts are never part of that. Remember? They're not consumed. But we haven't talked about anti-sin.
Okay? So what's the product? By the way, here you start with an alkene, yes?
Uh-huh.
And what do you get as a product?
Alcohol.
An alcohol. Before we started with an alkene for the Br2, we got a vicinal dihalide. For the HCl, we had an alkyl halide, yes? And for this one, we get an alcohol. We redraw this, yes? Or no?
Yeah.
Yeah.
Without the double bond. And then the methyl group.
Oh, you got that?
The methyl group, yeah.
Okay, so the one with the more hydrogen.
Okay, let's put something here.
That's why you got the OH on the bottom.
Yeah.
Put something there.
They can't see.
Who can't see? Because my broad back?
You added another.
I added another horn on that thing.
It won't matter.
Okay? So, this is just, don't worry about what that is there for. So, where's the hydrogen going to go?
On the bottom of
The
that double,
hydrogen's
right
gonna go
there.
here.
Yeah,
Because
because it has the most hydrogen.
this has a hydrogen already. According to
Yeah.
Kornikov addition, it will go to the
The bottom.
hydrogen with more hydrogens.
Uh-huh.
Where did that methyl group go?
It has so much for both
It hasn't gone anywhere. I'm not done.
So then that's going to be a
So,
carbon kind of.
the hydrogen went here because my Kornikov addition says that
It has to go to the one with the most
it goes with
hydrogens.
the one with most hydrogens. So why does it go to the one with more hydrogens? No, not because I said.
Stability?
You just got here. Why are you talking?
Yeah, what the tutor?
Yes, it is true.
That was
It's
good.
because of carbocation.
Correct.
split.
Yeah.
What? Because it forms a more stable carbon
Yes. Yeah, everybody has a short bladder. So the carbocation was here.
Yeah.
So now the OH is going to go here,
Uh-huh.
right? I didn't have a plan to this. Now here's a problem, yes? This carbon here has that group, it has this group, and it has that group.
Right.
They're different groups, are they not?
Mm-hmm.
They're different groups. What that means is that this carbon is
Chiral.
So I notice now that that carbon is chiral, so I have to draw what? I have to draw an enantiomers of this. So instead of I'm going to draw that. Yes? The hydrogens here don't make a difference, yes?
No.
So I didn't draw them. On one side, you're going to have the CH3, and on the other side, you are going to have
OH.
the OH. Yes or no?
Yes.
And then you are going to draw the other one, in which
It's opposite.
on one side you have the OH, and on the other side you have the
CH3.
CH3. What are they of each other? They are enantiomers. What type of product is this? This is a racemic mixture. This is a racemic mixture because the product was chiral. Yes?
Yes.
Do we not need to draw out the additional hydrogen we added?
You don't need to draw it. I mean, you could if you wanted to. You guys want the mechanism for this? Outstanding. All right. You know what? Before I give you the mechanism, let me give you another reaction that is not in the book. You want it? You want stuff that is not in the book? Provide the product for that. This is catalyst, yes?
Yeah.
See how many of you read about this reaction.
How are we going to read about it?
Oh, I'm never asking about that. And
You just said that.
You could have read about it because you could have gone to another 2 or 3 different books. You only using one book for this class?
Professor, when you drew the end racemic mixture, you didn't include the additional methyl group.
Oh yeah, because I forgot it, so you put the additional methyl group is here, yes?
Yeah.
And you added that so it becomes a chiral center, so it has the enantiomers, right?
All right. So what's the answer to this? What happened? Here's an OH, yes?
Yeah.
And this, like water, yes? The H added to one side and the OH added to the other side. Here the H adds to one side, and the O, it just happens not to have an H here, has a CH3 added to the other side. This is an ether.
Ether. Yes, ma'am.
Yes?
Yeah.
The same type of reaction, not in the book, I don't think. I haven't seen it, but then I haven't looked carefully.
And for this one, we don't worry about the anti-arsen, right? Instead of the previous one.
I don't know what you're talking. I haven't talked about anti and sin, yes?
Yeah, we did. We thought we were talking about anti-arsen.
I think this is anti or sin?
No, but at the beginning of the lecture, we were labeling it as anti.
For the bromonium, yeah.
Right. And so it's only, the anti and sin is only when it's halogenation.
There is no anti and sin here, right? Because it's from the top and from the bottom, yes? Formation of a carbocation. Yes? It's planar. So here is a mechanism for hydration. We have our famous alkene. The sulfuric acid, what it's going to do is it will protonate this water, yes? There's H plus running around. So that is going to get that, and it's going to form this thing. Yes or no? It's just H plus, okay? But I didn't want to just draw H plus. So the double bond is going to do what?
Right.
Attack
Attack what?
the positive.
attack
The negative.
The hydrogen.
the hydrogen, of course. And can this bond stay here?
No.
No, that bond is going to break, and the water is going to keep the electron. Yes?
Yeah.
This here, after it does the attack, is going to form water again.
Mm-hmm.
So what you are going to get is bond there, bond here, and here. And now you are going to have a hydrogen there. Any formal charge anywhere? Here there is a formal charge, yes?
Positive.
Yes or no?
Yeah.
Every time you form a carbocation, there is a possibility of a racemic, but also a carbon chain rearrangement. So let's say that this was a primary carbocation, and here there were methyl groups here. What would happen is maybe one of these methyl groups will migrate here, or one of the hydrogens will migrate. Okay, in a methyl shift or
Hydride shift.
hydride shift. Every time you form a carbocation, that could happen.
Right.
Okay?
Right.
So, this is positive, and now, guess what there is a lot of in here? There is water. Yes? What is the water going to do?
It's going to attack
Gonna
that
attack
positive.
It's going to attack that. And what you are going to form is with the electrons from water, yes?
Mm-hmm.
H and H. Yes or no? Any formal charges here?
Plus.
Yes, plus on the
Plus where?
oxygen.
Plus here. Now that is not going to stay like that. So what happens is another water molecule, and you have to remember this. Another water molecule is going to do what?
Attack.
Is going to
Attack the hydrogen.
get this hydrogen,
Hydrogen. It's going to
and
make H3.
Trans-
this
Transport.
electron pair
It's gonna
is
go
going
down
to go to
oxygen.
that oxygen. Okay? So what this is going to give you after that happens is
OH, H,
hydrogen here,
OH, and hydronium.
that's the two electron pairs, plus this electron pair from here,
Yeah.
plus that hydrogen. That is the alcohol.
Uh-huh.
And what else did it generate?
Hydronium.
Yes, hydronium. This was like that before the water picked up the hydrogen. Once it picks it up, one of these electrons was used to make that bond, and this is once again H3O plus. And H3O plus was the beginning of this thing.
Yeah.
This is why we only need catalytic amounts of sulfuric acid. Okay? Yes or no?
Yes.
Wait, can you explain that last part one more time?
Which is the last part?
That last part.
The one that I did over here or the one that I did here? Here?
Yeah, like from the transition from this to that, because you said, okay, don't forget there's another molecule, okay, I got that, another water molecule.
Yeah, this water molecule, because there are many around, this water molecule will pull this hydrogen off. The electrons will go to that oxygen to form two electrons from there, and now these two that are from here will give you just a regular alcohol, not protonated, this was protonated. And now the water is going to pick the hydrogen, so it's going to become H3O plus, yes? And this here is the beginning of this, yes? So the H plus is regenerated, yes or no? It's regenerated and it begins another cycle, yes? That's why you only need catalytic amounts. Is the mechanism for this different from that one? Mechanism for this different from that one? No. Instead of having an OH over there, what do you have? CH3. So instead of being this OH here, so CH3 and CH3 and a CH3 and a CH3 and a CH3 and a CH3. Yes?
What's that thing that's right on the top?
What's what?
The first green on the top.
The first what?
Green.
Green?
Yeah.
Water?
Yeah, we're water in the packing the. No, it's being protonated.
Yes, it's
But
being
it's the fluid
proven.
packing. Oh, and then everything else starts.
Okay, guys, what's up?
I have a question.
Yeah.
Does this one rotate or no?
That's what?
Rotate and become anti or?
It's what?
Do those phones rotate and become anti or no? It's more stable than deformation.
Yeah, I mean, if remember, I did not put any groups here, yes?
No.
I didn't put any groups. Yeah, this is rotating like we did before. The Newman projection.
But
It was all SP3, so.
it's more stable.
It never stays there.
Oh.
And remember, it's rotating, like the way we show. Yeah, it's more energy when it's eclipsed. It's less energy when it's anti, but they're still rotating. Okay, let me give you, you want a test question?